Lesson is about how derivatives affect the shape of a graph. As always, if you think my video is helpful to your learning, please give me a like, click the subscribe, and share this video out. In the previous lessons, we already discussed first derivative, f prime of x. What is first derivative about? Every time you hear the word first derivative, f prime of x, the first word that comes into your mind is slope, right? So maybe in an application problem, you are thinking about rate of change. The rate of change basically is slope. So finding using the slope, we can determine the minimum, the maximum of a function. So what do you see in the problem? The problem will give you a function, f of x. So we have f of x. If you plug in an x value into the function, then you get the location, the xy coordinate of a point. To find the slope, first you take the derivative. So you find f prime of x, and then you set that equals to 0, and then you solve for x, and those x values, they are critical points. So sometimes f prime of, so you will get x equals to c, right? And this value, we call that critical points. So sometimes f prime of c is equals to 0, and then sometimes f prime of c is undefined. What is undefined? So when f prime of c is undefined, you either have a cups or you have a sharp point. F prime of c is equals to 0, so that means x equals to c. This x equals to c is a critical point. And you might ask me, hey, I see you write second derivative f double prime of x on this notes. Yes, in this video, we are going to compare the first derivative and second derivative. So based on everything we learned so far, first derivative is about slope. You use the slope to find the local maximum, to find the local minimum. But for the second derivative, we are going to find concavity. And then concavity, a function can be either concave up or concave down. But first, let's review the concept of first derivative, and then we will go over to the second derivative. So we have x equals to c equals to is a critical point, and then how do you find a local maximum? So to find a local maximum, first when x is less than c, right, you test a test interval. You have increasing, right? When x is equals to c, you have a horizontal tangent. When x is greater than c, you have a function decreasing. So going up, horizontal, and then going down. So at the top of the mountain, we have a maximum. At this point, f prime of c is equals to 0. So we have a local maximum. So looking at a graph, local maximum, that is a parabola facing down, looks like this, and then this point is a local maximum, and then at the maximum, we have a horizontal tangent line. What about minimum? The slope, in terms of the slope, so the slope first decrease, and then horizontal, and then increase. So this is the bottom of a hill. This is a minimum, and then at this point, we have f prime of c that is equals to 0. So using a graph, we have a parabola, looks like this, and then at this point, we have a minimum. And then at that point, we have a horizontal tangent line. So maximum, minimum. What about f prime of c is undefined, the cups and sharp point? So for a maximum, this can be a maximum, a sharp point. So at this point, we have a maximum. Or we have this, we have a curve looks like this, we have a curve looks like this. This is a cups. The first point is a sharp point, the second point is a cups. So this one is cups, and then this one is called a sharp point. What about minimum? Minimum can be this. At this point, f prime of c is undefined. This is a sharp point, and this is a minimum. Or you have one curve and then another curve. At this point, we have a minimum. This is a sharp point, and then this is a sharp point, and then this one is called a cusp. What about second derivative? Let's take a look at the second derivative. So second derivative, let me switch color for second derivative. Second derivative helps you to find concavity. So concavity, this might be your first time using this word concavity, and then for concavity, a function can be either concave up or concave down. So what is concave up? So concave up is this. So the best way to think about concave up is using a parabola. A parabola, the U shape is facing up, just like a bowl, is facing up. So that is concave up, and then this is concave down. The U shape, the U is facing down. And then any other good picture to picture concave up? Yes, there is a pretty good picture that I want you to memorize. Do you use emoji when you chat on your phone, when you chat online? Emoji. So concave up is a happy face. So happy face. Look at it. Look at the mouth. Smile. Right? Happy face. Concave up. Sad face is concave down. So this is a sad face. Concave down. Right? Concave up. Concave down. How do you get to the second derivative? First, the problem will give you a f of x. And then you have to do f prime of x. So that helps you to find the first derivative and the slope. But we are not talking about slope at this point. We are talking about f double prime of x. So f double prime of x. F double prime of x. So this is what you have to find. And then we need critical point as well. So you have to set this equals to 0 and then solve for x. So x equals to c is also called a critical point. Critical point. So here is how you do the concavity. So let me draw a number line. So number line, you can imagine, treat that as an x-axis. So we have a number line, or you can call this an x-axis, horizontal axis, and then we have x equals to c as a critical point. And then when x equals to c, there is x equals to c. If you plug in x equals to c back to f of x, you get a point on the curve, right? It's a point on the curve. What about this interval? This is from negative infinity to c, and then this is from c to positive infinity. So we have one line, we cut the line right in the middle, we divide the line into two intervals. Another way to say this is x less than c, x equals to c, and x greater than c. All right, so what happened if I have f double prime of c greater than 0? When the second derivative is greater than 0, the function is concave up. So concave up looks like this. It's a U shape facing up. So this one is concave up. And then what about concave down? When x is greater than c, we have f double prime of c is less than 0. So we have a concave down. Then we have this. This is a concave down. What about this point? The point where the up and down or down and up changes. So this x equals to c, this one, we call this an inflection point. Inflection. What about from concave down to concave up? Same thing. So let's switch color for this one. Let's say f double prime of c, just a what if. So f double prime of c is less than 0. Then we have a concave down. At x equals to c, f double prime of c equals to 0. We have a critical point. F double prime of c is greater than 0. We have a concave up. So concave down, right? So this is a concave down, and then concave up, and then x equals to c. We have an inflection point. So first we start with a concave down. So that is a concave down, and then at x equals to c, we have an inflection point, and then when x is greater than c, we have a concave up. So this is going from down to up. And then at this point, the big red point right there, we have x equals to c. That point, we call that an inflection point. So that is the comparison of first derivative and second derivative. Again, for the first derivative, what we are doing is we are finding the slope. Using the slope, we can determine the local max and local min. The second derivative is concavity. The function is either concave up or concave down. All right, so that is the comparison of first derivative and second derivative. In the next video, I will give you some actual examples. I will see you in the next video.